As you can see, we're going to discuss polar coordinates, and in a calculus course, this is really expected to be a review. You should have hopefully seen polar coordinates in an earlier algebra class or a pre-calculus class. So this will be rather quick, and assuming that you have some familiarity already. So the idea here is that we're used to a rectangular coordinate system, and we understand a rectangular coordinate system. We have a vertical axis and we have a horizontal axis. And of course, normally we're calling the horizontal axis X, normally calling the vertical axis Y. Now, in polar coordinates, remember we have a pole that we have what's called a pole, and we have a polar axis. So let me just remind you, in polar coordinates, we have a pole and a polar axis. Polar axis is a horizontal line from the pole. So that positions the pole, of course, and this whole axis is supposed to be horizontal, is called the polar axis. Of course, we understand that this position we call the origin when we're talking about rectangular coordinates. So, a matter of convenience, we actually transpose, if you will, that pole and polar axis on top of the rectangular coordinate system, where the pole is right here at the origin. And so the polar axis corresponds to the positive x-axis. That is, the polar axis is along here. Okay, same as the positive x-axis. Okay, well, here's the idea then, kind of the marriage between these two systems. We have a point that is in the plane. I'm showing it in the first quadrant just as a matter of convenience. If we draw the ray that goes from the origin or the pole through that point, okay, that forms an angle. And we call that angle theta. And the distance from the pole to the point in question, we're trying to identify this point. The distance from the pole to the point in question we'll call r. That distance is r. So in polar coordinates, we refer to that point as the point that is r units from the pole or the origin. That's an r, lowercase r. And the angle that ray makes with the positive x-axis or the polar axis is theta. So that's the way we can identify or locate that position using polar coordinates. That's what these are. Okay. Now, we also know that we can identify that point as with rectangular coordinates, and I'm going to call those coordinates x comma y, which would mean, here's another important part of this, though. If I were to create a right triangle by dropping a vertical from that point down to the x-axis, then we have a right triangle where the hypotenuses are, and one of the legs is x, that distance is x, and the other leg is y, that distance is y, and so we kind of have a marriage between these 2 points. Because we have a triangle, a right triangle, that kind of brings them together. Now, if you recall, here are the important pieces of that marriage. Because r is the hypotenuse of that right triangle, and the legs are x and y, then because of the Pythagorean theorem, we know that r squared is equal to x squared plus y squared. Now, sometimes we'll write that as r is equal to the square root of x squared plus y squared. And if you recall, though, r may be negative sometimes. We'll see that later on. Another thing that we could say here is that the tangent of the angle theta, well, how do we calculate tangent of theta when we're dealing with a right triangle here? Well, it's opposite over adjacent. So the tangent of the angle theta is y over x. And those kind of go together. And those are 2 pieces that are important and they kind of go together. Now, there's something else that we can do here, though. Notice that the cosine of theta, okay, the cosine of theta is, well, what is cosine? It would be adjacent over hypotenuse, so that's x over r. Now, what that does, what we can do from that is we could multiply both sides by r, and we would get r cosine theta is equal to x, or more importantly, x is equal to r cosine of theta, r times the cosine of theta. In a very similar fashion, we could say, oh, well, look at this. The sine of theta, well, sine of theta would be opposite over hypotenuse, so that's y over r. And when we multiply both sides by r this time, we'll get r sine theta is equal to y, or y is equal to r times the sine of theta. Now, these are also very important, okay? We want to keep in mind we will use these in some instances, this pair of relationships, and we will use these relationships in other pairs of other situations. And one of the first ways that we use them is if we want to convert from one system to another. That is, if we had some point that was in polar form, and we wanted to convert that point to rectangular form. Well, if it's in polar form, then we're given something that looks like an r comma theta, okay, if it's in polar form. And what we want to do, of course, is change that to x comma y. Well, to do this, you can see real clearly that, oh, if we know r and theta, and that's the form that we've got, if we want to do that, then to calculate x, we simply need to use the fact that x is r times cosine of theta. And to calculate y, we simply want to use that y is equal to r times the sine of theta. So this is an easy operation. So suppose r is 4, and suppose theta is pi over 6. Well, to do the conversion, what would we do here? We would come down and would say, okay, to calculate x, we would say 4 times, well, we would say r times the cosine of theta. And so that would be, our r value is 4, and our theta is pi over 6, so we'd say 4 times cosine of pi over 6. And we'd do a quick calculation here. What is the cosine of pi over 6? Well, we may forget, but it's the square root of 3 over 2, isn't it? Square root of 3 over 2. And so when we simplify that, we get, what? 2 times the square root of 3. That's our x value. 2 times the square root of 3. Now, on the other hand, when we want to calculate our y coordinate, we would use y is equal to r times sine of theta. And of course, r is 4, and theta is pi over 6, so we'd have 4 times sine of pi over 6. Well, sine of pi over 6, I believe, is 1/2. So we'd end up with 4 times 1/2, or 2. And so our y-coordinate would be 2. Okay. So we've made the conversion from polar coordinates to rectangular coordinates. This is coordinates to coordinates. Now, just as a little side note here, let's think about, okay, let's think about if we were doing this with polar coordinates, just roughly. Okay, just roughly. Here's my polar axis. I mean my pole. Here's my polar axis. Okay. And here's the way I would graph that point. I first have to figure out where the angle pi over 6 is. See, we write it the r first and the pi over 6, but how far is r? Where is r if we don't know the angle that we're working off of? So we go to where the angle pi over 6 exists. Okay, and pi over 6, we'll say roughly is along here. So we go think about this angle. Okay, that's the pi over 6. And we need to measure off a distance of 4 units along that angle. Okay, so we'd say here's 1, here's 2, here's 3, here's 4. That's roughly where that point is. Now, if we were using rectangular coordinates, let's think about that. If we're using the rectangular coordinates, well, 2 times the square root of 3, the square root of 3 is about 1.7. So if we take 2 times that 1.7, we would be about, about 3.4 units. So we would say, here's 1, here's 2, here's 3, here's 4, and if we're about 3.4, we'd say roughly in that position. And we're going to go up 2 units. Well, let's see, there would be 1, there would be 2, okay, so up 2 units, and there would be that point right there, which in rectangular coordinates is 2 times the square root of 3, comma 2. Over here, remember, in polar coordinates, this was 4 comma pi over 6. So we get to the same location, we just do it in a different way. Now, converting from polar coordinates to rectangular coordinates is relatively straightforward. But sometimes we get in a little bind if we're converting from rectangular coordinates to polar coordinates. So let's go through that on the next page. As I was just saying that when we're converting a rectangular form of a point to a polar form, it's a little more difficult. We have to be more careful, I should put it that way. So we have something that is in form x comma y. And we need to convert that to something that is in the form r comma theta. Now, that means we know x and y, but we've got to calculate r and theta. And so on the previous page, as we started this out, we came up with the fact that 2 important things, that r squared is equal to x squared plus y squared. So that is, if we know x and y, we can figure out r squared. Or maybe more importantly, r is equal to the square root of x squared plus y squared, or at least we can use that. And we still need to know theta, and on the previous page, there was a relationship between theta and x and y, okay? If we used what we used a moment ago, we said x is equal to r cosine theta, and that's just a relationship between theta and x. I suppose we could use that, but more naturally, more likely, what we're going to use is the fact that the tangent of theta is y over x. So it's these 2 pieces that we're going to use to do our conversion, if you will. So as we go through to do this conversion, let's look at an example. Let's convert the point, the rectangular point, -1, 1 to polar coordinates. So we got to figure out what r is, and we have to figure out what theta is. Now, by the way, before I go on, I'm calling these the rectangular form. Sometimes it's also called the Cartesian form. And either one is appropriate, okay? Either one, that's the same thing as rectangular form. And I guess historically it's probably actually been called the Cartesian form because that's named after a famous mathematician, René Descartes. He's actually the one that proposed or started this idea of something like an XY axis system, a rectangular coordinate system named after him, Cartesian. Okay, well, let's go back down to this problem that we're working on. And you can see it would be real easy to calculate r, because all we need to do to find r is say that it's the square root of x squared plus y squared. And so in this case, r would be the square root of -1 squared plus -1 squared. And that ends up just being the square root of 2. So we have our r value very quickly. Now the theta value is a little more difficult, because what we know is that the tangent of theta is equal to -1 over -1. And of course, that's just equal to 1. So we have the tangent of theta is equal to 1. Now, I've got an example here where it's fairly simple and routine. Here's the problem, though. There's lots of angles that have a tangent of 1. There's a lot of angles. If you use your calculator, okay, you're not necessarily going to find the angle theta. So what I'm going to say here is you would find some angle, I'm going to call it theta hat, by taking the inverse tangent of 1. You've probably been through this in trigonometry. And if you do that, you'll get pi over 4. Well, that's true, because the tangent of pi over 4 is equal to theta. Is equal to 1. Unfortunately, this is not the correct theta for us. And what becomes critical here is really recognizing where our point is. See, we have a point that has rectangular coordinates -1, comma, -1. Well, that means we go to the left 1 unit and we go down 1 unit. And so our point's actually down here, isn't it? Now, if we were to draw the line of connecting the pole or the origin with the point in question, and we look at the angle involved, well, the angle theta is always measured from the positive x-axis. So the angle theta is actually this angle right here. That's theta. Oh, well, that's certainly not pi over 4, is it? In fact, we could figure out that that angle is, what is that angle? That angle is actually 5 pi over 4. What our calculator told us is it gave us this angle that I'm writing dash there. See, it gave us this angle. That's theta hat right there. And the reason that happens is the inverse tangent function. Our calculator didn't do anything wrong. Inverse tangent function always gives an answer between negative pi over 2, negative 90 degrees, and positive pi over 2, positive 90 degrees. So it's always given us an angle that lies like this. See? It's always an angle in there. And so it would never give us the correct angle over here. So we have to be somewhat understanding of what angle we really are at, or what quadrant we're in, so we can finish this idea. Well, our theta is actually, what we had was a reference angle there. Theta hat's a reference angle. But with a little more information, we can figure out that theta is actually the angle 5 pi over 4. Okay. And so now we have done that conversion. Well, that's the issue with converting from rectangular to polar. Using tangent of theta as y over x isn't always going to be the best thing. I mean, we may have to add some information to it. So let me summarize real quickly here. Converting points. Converting points. And we're talking about from rectangular to or Cartesian, rectangular to polar, or polar to rectangular. So the easy type is polar form to rectangular form. That means we're starting with an r comma theta, and we're going to an x comma y. Well, this is easy because we simply use x is equal to r cosine theta to calculate the x, and we simply use y is equal to r sine theta to calculate the y. So when we're doing that conversion, it's relatively simple. When we're converting from rectangular form to polar form, we're starting with a point in the form x comma y. So we know our x and y value. When we're done, we need to have a point listed as r comma theta. Okay. Well, here we can calculate r relatively simply. We can say r is the square root of x squared plus y squared. Since we know x and y, this is simple. Now, for theta, we have to say, oh, the tangent of theta is equal to y over x. But using our calculator and coming up with inverse tangent of y over x is not always going to be appropriate or accurate, maybe I should say. So when we're using this, we need to be careful. Well, in a way, I guess I've gotten the cart before the horse, because what I'd really like to do is plot some points now. And we've done some converting, but I'd really like to plot some points to make another point, pun not intended here, about how polar coordinates are different than rectangular coordinates. And so I'll do some plotting of points on the next page. As I just mentioned, I want to plot some polar points because that gives us a different set of information about how polar coordinates are different than rectangular coordinates. And by the way, one of the reasons I suppose these are called polar coordinates is I'm not so lucky here to be able to draw this, but there's actually graphing paper, like there's graphing paper that have grids on them so you can mark off x, y values pretty easily. There's also graphing paper where you have a pole and the polar axis, and I'm going to kind of lay this back on top of a rectangular coordinate system, and what you see is a bunch of concentric circles. Like you'll see a circle that'll look like this, and then you'll see a circle that'll look like this, and then you'll see a circle that'll look like this. Now, the significance is each of those circles, the little circle has a radius of 1, and or whatever we want to call it, and the second circle has a radius of 2, or whatever we want to call it, and the third circle has a radius of 3, or whatever we want to call it. The idea is that if we're measuring along an angle, we can think of this as 1 unit, this is 2 units, this is 3 units, or we could say 2, 4, 6. Or we could say 0.5, 1, and 1.5. We have some kind of grid in this form that would allow us to do that. And so if we look at different angles along here as well, so if we look at different angles, then what's going to happen is it looks kind of like we're looking down at the Earth from maybe at a globe, if you will, and we're seeing lines of longitude and latitude. That's the idea of this. This looks like looking at the North Pole from outer space if we were looking at a globe. That's the idea behind it. Anyway, I'm not so fortunate, so what I'm going to do is just lay these on top of a rectangular coordinate system. So this point 1, let me label them this way so I won't have to put these on the graph, the coordinates on the graph. So I'm laying out what looks like a rectangular coordinate system, but I'm really thinking of a polar coordinate system, okay? Really thinking of a polar coordinate system where here's the pole, and of course the polar axis matches this positive x-axis, okay? So the way we plot a point in polar coordinates is that we first locate the angle. So in this case, on number 1, the angle is pi over 6. And pi over 6, remember, is about 30 degrees. And so I'm going to draw the angle in here, and I'm just roughing it in. That looks like that's about pi over 6, okay? Now, the next thing we do is we look at our R value, and we measure, in this case, 2 units along the angle where the initial point of the angle is the origin, and the 2 is positive, so we're going to go in a positive direction. Well, here's the position, let's say, here's 1, here's 2. So that's 2 units along the angle pi over 6, and so that's the first point plotted. Now on the second point, the angle is negative pi over 6. Well, that means, remember, we're always measuring from the polar axis, or the positive x-axis. So if we're negative pi over 6, we go in the opposite direction. Negative pi over 6 would be roughly this angle. You know, just roughing it in here, roughly this angle. Okay, so that's the angle. Let me write it out here so I have enough room in there. That's an angle negative pi over 6. Now, my R value is 2 again, and so I measure along that angle, okay, I measure 2 units. There's 2 units. So this is the point, the second point, 2 comma negative pi over 6. Now the third point throws things off a little bit. On the third point, okay, our angle is pi over 6. And we've already drawn in the angle pi over 6. But the problem is that that angle, if we're measuring our units that are positive, then we measure along that angle. See, we're measuring along this angle if R is positive, but, oh, R can be negative. Okay, I didn't really say that earlier, but this you should remember. R can be a negative number, and that means we have to, it's based on direction. If R is positive, we follow the angle. If R is negative, then we go in the opposite direction of that angle. So we would be coming in this direction, whoops, instead of the direction we were going a while ago. So in this case, our negative 2 makes us go, instead of to the right, if you will, to the left. So we measure 2 units along here, and that's where that point would be. That's point number 3. The angle is pi over 6, but the R value being negative 2 means we go in the opposite direction. Now, that brings up something else that's interesting, okay, because if we look at that point 3, we could have gotten to that point 3 in a different way. We could have measured the angle from the positive x-axis, okay, to there. And that angle is actually 7 pi over 6, isn't it? I believe that angle is 7 pi over 6. And then we could say, oh, well, let's go in a positive 2 direction. So that point, 2 comma 7 pi over 6, puts us in exactly the same position as negative 2 comma positive pi over 6, okay? Those two notations put us in the same location, and that's that point 3 that we've already got labeled there. Okay, well, let's go back now and let's look at a couple of more points. That is, I want to make a note here. The point 5 comma pi over 3 and the point 5 comma negative 5 pi over 3 and the point negative 5 comma 4 pi over 3 and the point negative 5 comma negative 2 pi over 3 all put us in the same location. Every one of them is in the same location. So let's just go and look at this. For the very first point, okay, well, our angle value is pi over 3, and pi over 3 is roughly here, okay? That's roughly pi over 3. And if I measure 5 units out, let's see. Here's 1, here's 2, here's 3, here's 4, here's 5. So we're talking about this point. Now, if I look at negative 5 pi over 3, let's see. That means I'm measuring in this direction, doesn't it? And I know that if I go, I'm counting these off, but you would need to verify this. If I go to here, well, that's negative pi, which is negative 3 pi over 3. And then if I go a negative pi over 3 again, I'll be at negative 4 pi over 3. Now what I'm getting at is this angle right there is negative 5 pi over 3. So we're actually don't have the same angle, but we have the same initial point and ending point, if you will. Okay, initial and ending. We get in the same angle or the same ray. So when we go 5 units along that direction, we're still at the same position. Now, on the other hand, 4 pi over 3, the angle 4 pi over 3, well, the angle 4 pi over 3 ends up being right here. Say the angle 4 pi over 3 would put us right there. That's 4 pi over 3. So if we think about that angle, but our R value is negative 5, that means we don't go in the direction of that angle, we go in the opposite direction, 5 units, so that puts us right back to this position. Or we could look at the angle negative 2 pi over 3. That's for this last point. The angle negative 2 pi over 3 puts us right here. That's negative 2 pi over 3. Well, if we look at that angle, and our R value is negative 5, so that angle's here, isn't it? Right there. Okay. And if our R value is negative 5, we don't go in this direction, we go in the opposite direction. So we go 1, 2, 3, 4, 5 units. That's negative 5 based on that negative 2 pi over 3 angle. We're right back in the same position. Now with rectangular coordinates, an x comma y is unique. There's not two x comma y's that give us the same location. But with polar coordinates, there's an infinite number of ways by just changing our angle. Going around multiple times would be another way to get to that position. But what we prefer, okay, let's put it this way. What we prefer, and if we use this, then it's unique. We prefer 1 for the R to be positive. And we prefer 2 for the angle theta to be between 0 and 2 pi. It doesn't need to be equal to 2 pi because theta equal to 0 gives us the same position of theta equal to 2 pi. So our preference is to have thetas and r's that follow these two conditions. And if they do, then our polar points become unique. The coordinates are unique then. Okay, well, next I want to talk about polar equations as opposed to rectangular equations and how we can convert those from one system to the other. So we'll start that on the next page as well. Our discussion about polar equations is to first just recognize the difference between polar equations and rectangular equations. Whereas rectangular equations have x and y. Okay, so a rectangular equation, let's say just an equation, might be something like 3x minus y is equal to 2. Excuse me, plus 2, pardon me, plus 2 is equal to 0. Well, we might recognize, and I hope that we would, that that's the equation of a line. A polar equation, and usually we like to say y is equal to, so obviously we could rewrite that a little differently, and we could say y is equal to 3x plus 2, and then we more readily would recognize it as that of a line. Polar equations, of course, have r's and thetas rather than x's and y's. And just like with the rectangular equations, sometimes we prefer to have it written as r is equal to, like we would prefer to say y is equal to. We can't always easily do that. but occasionally we like to. So, for instance, R is equal to, let's say -2 divided by 3 cosine theta minus sine theta. That's an example of a polar equation. Now, what we find in this study, and later on how we'll use this, is that many times a rectangular equation is very, very complicated. And if we can convert it to a polar equation, it ends up being very, very simple. On the other hand, sometimes we have a polar equation that looks very, very complicated. And the rectangular version of that, if we converted, would be very, very simple. So it's useful to be able to move from one system to the other. So that's what we want to do now, is we want to convert equations from one system to another. So the first example, this example maybe doesn't well, I tell you what, let's use this first example. Convert, okay, this is our problem, convert y is equal to 3x plus 2 to polar form. Now, when we're converting from rectangular, okay, to polar, when we're doing points, that was complicated. When we're doing equations, it's simple, because every time we see an x, we can replace it with r cosine theta. And every time we see a y, we can replace it with r sine theta. So this ends up being a fairly simple proposition when we take the equation y is equal to 3x plus 2. We're going to replace our y with r sine theta equal, we're going to replace our x, well, we have 3 times x, we're going to replace our x with r cosine theta, and then plus 2. So we've done a conversion from one system to the other. Now, the next thing, though, we may want to do is we may actually want to solve it for r, like I said, so we can say r is equal to. So here's what I'm going to do. I'm choosing to do it in this particular way, so I can show you what I had above. I'm choosing to do it in this particular way. What I'm going to do is leave 3r cosine theta on the right side. Okay, I'm going to leave it on the right side. I take that back. Yes, I am. And I'm going to subtract 2 on both sides, so I have a -2 on the left. And I'm also going to subtract r sine theta on both sides. So I'll have 3r cosine theta minus r sine theta over here on the right-hand side. Okay. Now, the reason I've done that, maybe I should have explained myself a little better, and I did not. If I'm going to solve this for r, what I need to do is get all terms involving r on one side. And I chose to get them on the right side in this case, just by happenstance, I suppose. So now, on this right side, I have an r that's a common factor in both of those terms. So I'm going to factor that r out. And I'm going to actually, well, we'll factor it out. So I have r times 3 cosine theta minus sine theta. Now, if I'm trying to solve for r, then I need to divide out this expression right here. So I'm going to divide on both sides by that expression, and I'll have -2 divided by 3 cosine theta minus sine theta is equal to r, or r is equal to -2 times 3 times cosine of theta minus the sine of theta. So you can see here we started with a line in rectangular form, and we've converted it to polar form. In this case, That's a little more complicated equation for a line, but it certainly is a line, and we could graph it if we so desired, but it'd be easier to graph the rectangular. Okay, let's look at another example here. Okay, this one we're converting the equation 4xy equal 9 to polar form. And by the way, that would be again, we're not really needing to do this, but what we would have here, if we solve for y, would be y is equal to 9 over 4x. And that's a rational function, and that's going to have a particular look. Just recall that's going to look something like this. Okay, that's all I'm getting at. It looks something like that if we were to graph it in polar coordinates. But that's really not the issue here. We're wanting to convert to polar form. So when we're converting from rectangular to polar, remember we're going to be able to do that easily at the conversion. We may have a little more work to do to simplify or put it in a form that we want. But x can always be replaced with r times cosine of theta, and y can always be replaced with r times sine of theta. So using that information, we can take this equation 4xy equal 9, and in place of x, we'll put r cosine theta. And in place of y, we'll put r sine of theta equal 9. And then, of course, what we see that we've got there is really a 4r squared times cosine theta times sine of theta is equal to 9. And that is certainly an expression that we could leave. We could simplify this a little further. Okay, we could simplify this a bit further. And to simplify it further, what we need to do is recognize, here's what I'm suggesting. Recognize that embedded in the left side, we actually have a 2 cosine theta times a sine theta. See, we could write this, there's nothing maybe wrong with where we are, but what we could do is we could write this as 2r squared times 2 cosine theta sine theta is equal to 9. Now that 2 cosine theta sine theta, let me rewrite that differently. That's the same as 2 times sine of theta cosine of theta. And the reason I've done that is that reminds me of an identity. And that identity is the sine of 2 theta is equal to 2 sine theta times cosine theta. So it would be useful here then to make this look simpler, I suppose, if we replace that with just one function rather than 2. So we could rewrite this as 2r squared times the sine of 2 theta is equal to 9. And that's a conversion for what we started with, okay? And I kind of like this answer better than the answer above because we only have one trig function involved in it. Okay. Well, next we want to do conversions in the other direction. Probably we would actually be involved in that more often. And so let's start with this one. How about we want to convert r is equal to 4 over 1 plus sine of theta to rectangular form. Now, here we have to work differently. We have to work a little more I don't know what I'm trying to say here. Sometimes we have to be a little more efficient or a little more clever. And because we only have so many tools. I mean, what we're trying to do is get x's and y's. And I suppose if we had an r squared, we can replace that with x squared plus y squared. So that's one thing we could do. Let's see, if we had, if we could create situations where we had something like r times cosine theta, then we could replace that with an x. And if we could create situations where we had something like an r sine theta, then we could replace that with a y. So there are things that we can do, but you know, right off the bat, we don't see anything in this first example, except what if I took that equation, and we don't like fractions, so what if I multiply both sides by that denominator? So on the left side, I'd have r times 1 plus sine of theta. And on the right side, I'd just have a 4. Now, the significance there is that if I multiplied that r out, I would have r plus r times the sine of theta is equal to 4. And the r times the sine of theta can be replaced with a y. So now I have r plus y is equal to 4. Now here comes maybe a clever part. That wasn't particularly clever. But if I subtracted y from both sides, then I have r is equal to 4 minus y. And the reason that that's significant for me is now, if I could create an r squared, I can replace it with x squared plus y squared. And I could create an r squared by squaring the left side. Well, that means I'd have to square the right side as well. Okay, well, that will create my r squared, and on the right side, I'll end up with 16 minus 8y plus y squared. And on the right side, since I have r squared, I can replace that with x squared plus y squared is equal to 16 minus 8y plus y squared. So let's see. You know, I'm probably not going to be in a position, I suppose I could actually solve that for y. But right now, let's subtract y squared on both sides. And if we do, then the y squareds are going to go out, and we'll have x squared is what, equal to 16 minus 8y. And maybe I leave it that way, and we would recognize that's a parabola, isn't it? Maybe we leave it that way, and that's probably okay. It's probably the way we ought to leave it. But we could go a little bit further, I suppose, and solve that for y. So what I would do maybe is subtract 16 on both sides. And then multiply both sides by negative 1/8. We could say multiply both sides by negative 1, but I would say negative 1/8. So I'd have negative 1/8 times x squared plus 16 over 8 is equal to positive y. Or I could write that as y is equal to negative 1/8 times x squared plus 2. And so we clearly see that we have a parabola. I'm not suggesting that we would necessarily write it in that way. This is probably okay right there. But that is a parabola we recognize immediately if we were to graph it. And so that tells us what we started with also, if we were to graph it, would have been a parabola. Okay. Well, let's look at yet another one. Here, let's convert, how about r is equal to, let's say r is equal to 5. And we want to convert that to rectangular form. Well, since what we just did may give us a hint, we don't have much to work with here. We only have an r that's showing up, okay? And to do something about that r, we prefer to have it as r squared. since we remember that r squared is the same as x squared plus y squared, and so we could use that conversion. Well, to do that then, what we're going to end up doing is we need to square both sides, okay? So we'll square both sides here. So we end up with r squared is equal to 25, and then r squared can be replaced with x squared plus y squared equal 25. And we recognize that as a circle. That's a circle that's centered at the origin and has a radius of 5, doesn't it? So centered at the origin has a radius of 5. So here we're 5 units out, here we're 5 units out, here we're 5 units out, and here we're 5 units out. Now stop and think about this equation r equal 5. That has no information whatsoever about the angle. So what it's telling us is no matter what angle we pick, we're going to go 5 units out. 1, 2, 3, 4, 5. No matter what angle we pick, we're going to go 5 units out. 1, 2, 3, 4, 5. And so regardless of the angle we're at, we're 5 units from the origin. And that certainly is going to give us a circle, isn't it? That's the equation of a circle. Now here's an example where the equation of a circle in rectangular form is not real complicated, but the equation of a circle in polar form, at least one centered at the origin, is very simple. What about, let's see, let's convert theta is equal to 45 degrees to rectangular form. Oh, well now this is another issue altogether, isn't it? We need to create x's and y's. And here's what I'm thinking. I can get x's and y's if I remember that the tangent of theta is nothing more than y over x. So why don't I take the equation that I have and say take tangent of the left side, and that'd be equal to tangent of the right side. And on the left side, oh, I can replace tangent of theta with y over x. And on the right side, I know the tangent of theta at 45 degrees is just 1. And so then I could multiply both sides by x, and I would have y is equal to x. So in this case, we actually have a diagonal line, don't we? Y equal x is a diagonal line. We've converted. Okay, let's do one more conversion. And this one probably is the most interesting of all of them for me because we're going to use it later on. So in this case, we're asked to convert the equation r is equal to negative 8 times cosine of theta to rectangular form. Now, we've been operating on squaring both sides, or a couple of them. We squared both sides so we could get an r squared. But that's just going to give us cosine squared on the right side, and that's not really going to help us a lot. So here we use yet a different technique, and it's kind of a sly technique, and that is that remember we could if we had r cosine theta, we could replace that with an x, couldn't we? And so I'm looking on the right side, and I'm saying I don't have r cosine theta. But if I multiply the right side by r, then I will have an r cosine theta. But if I do that, I've got to multiply the left side by r. And that has an added benefit because then I'll have an r squared. So what I'm going to do is I'm going to actually multiply both sides of this equation by r. And I would really make that decision based on the right side, wanting to create a situation where I had r cosine theta. Now, like I said, the benefit is on the left side, I now have r squared. On the right side, I can rewrite it as -8 times r cosine theta. And of course, r squared can be replaced with x squared plus y squared, and r cosine theta can be replaced with an x. Now, pardon me. We might say that's good enough, but the truth is, what we have here is a circle. Okay? And it may not look that way, but let me rewrite this a bit, because this is also important. And I'm wanting you to recognize later on that this equation is that of a circle. So that's the reason I'm going forward here. We normally wouldn't recognize to do this, but what I'm going to do is get all terms to one side. So I'm going to add 8x to both sides. Now, what I want you to remember is circles in general can be written in the form x minus h, the quantity squared, plus y minus k, the quantity squared, is equal to the radius squared. Okay, that's what they look like in general. And so what I'm trying to do is take the equation I have here and make it in that form. And that means this x squared plus 8x, I need to be able to change in a way so that I can factor and get something that looks like x minus h, the quantity squared. And that technique, remember, is called completing the square. So to complete the square on those two terms, x squared plus 8x, we need to add a 16. Now, how did we make that decision? Remember, we take the coefficient of the first degree term, that is the 8, we take the coefficient of x and divide it by 2, and that gives us a 4. And then we in turn take that 4 and we square it and gives us a 16. So to complete the square, we need to have a plus 16 there. But now we've changed the left side, so we need to, of course, add 16 to the right side. Now the whole point is that this x squared plus 8x plus 16 is a perfect square trinomial, okay? That is, we can factor it as x plus 4, the quantity squared. And then, of course, plus y squared we have out here is equal to 16. And so we could look at this now that we've done this, okay, we know that that's the equation of the circle. And we know that the center has an x value of -4, doesn't it? And a y value of 0. And we know the radius is 4. So we could actually graph that pretty quickly. Out here, let's say, is where -4 is. That's the center right there, -4 comma 0. And if the radius is 4, then the circle actually hits right there, doesn't it? The radius is 4, so we have a circle that looks kind of like that. And that's a real rough sketch. And in the next lecture, we're actually going to start recognizing that when we see something of the form we have there, that we can determine that we have that circle without going through this conversion.